Hello. I'm going to talk to you about projectile motion, but in particular, we're going to talk about things that are launched horizontally. So you could imagine like if you rolled a tennis ball across a table and then it fell off the table, that's as it takes off from the table, it's going horizontally. Or if you, any other situation, if you hit a baseball with a baseball bat and it initially came out totally horizontal. That's the kind of projectile motion we're going to start with because it's a little easier. So I'm going to call that a horizontal launch. Now, from your lab, what we should have understood is that projectile motion, when you have objects that are moving in 2 dimensions, well, if you're thinking, this free fall review, why'd we do that again? I didn't know how to do that. That was only for things moving in 1 dimension. In other words, you could set up a line, a number line, whether it's going up and down or sideways. And everything that we've looked at in physics so far has only been moving in a straight line. And now we're going to consider what about things that are moving in 2 dimensions. In other words, there's like an x and a y component to the motion. Okay, so what did we learn from the lab? We learned that in the horizontal direction, of course the horizontal direction is what we should call x, the position, which I'm going to call x, or how about if I call that x position, just to be very clear, which you probably measured in meters versus time in seconds. The horizontal position looks something like this. You got some points going like this. It was a straight line. What does that mean? Well, it means that a graph of x velocity, if position versus time is a straight line, then that means velocity is constant. Right? So in the horizontal direction, we have constant velocity. And we know how to do that. That's back to Unit 2. It kind of makes sense if you think about it, if you remember what it looked like, the video of that ball from above, like the drone footage of it. It looks like it's just might as well be rolling along the ground at a constant velocity. You can't see the up-down part, and it makes sense that since gravity is the only thing tugging on that ball downward, it makes sense that the velocity in the horizontal direction is constant because gravity's not playing in that direction. Gravity's only playing in the up-down direction. So whatever velocity the ball has in the horizontal direction, it's going to keep that. It's going to keep doing the same thing in that direction. So in the horizontal direction for projectile motion, we have constant velocity. And when we have constant velocity, remember, what equations do we have? We know that position, if you think about what would the equation for this line be, we have displacement is equal to the horizontal velocity, which I'm going to call Vx to make sure I understand that I'm talking about this x direction, divided by, times time. Times time. Or, of course, I was thinking about the Vx is equal to delta x over t, about writing it that way also, if you divided that over to the other side. And that's the only equation that you need to describe constant velocity. Now, in the vertical direction, which we're going to call the y direction, what did your position time graph look like there? In the vertical direction, the ball went up, then it came back down again. This is the graph of y position measured in meters versus time measured in seconds. It looked something like this. Right, ball went up and it came back down again. And when you graphed your y velocity, measured in meters per second versus time, it started out with a positive velocity. In other words, it was moving in the up direction, and then it got to its peak where the velocity was 0, and then it started coming down where it would have negative velocities. And you should have got something kind of like this. And oops. And if you found the slope of this would be the acceleration, and it would be about -10. So what do we have here? We have constant acceleration. And we know how to deal with that. That's back to Unit 3. And if we're only looking at the vertical direction, this is just a straight-up free-fall problem, which is why we did that little free-fall review right at the beginning of this unit. So constant velocity, maybe just to remind you, if you want to put a note here, that was Unit 2, and constant acceleration was Unit 3, just in case you want to go back and look at any of your materials from those units. And we might as well, I didn't ask you to do this for the lab, but if you were going to make a graph of acceleration versus time, that would be measured in meters per second squared. Then it would just be this at about -10, right? It's the slope of this. It's just constantly -10. Constant acceleration, get constant acceleration, -10. Now, what about equations for constant sorry, got hung up there. What about constant acceleration equations? Well, for constant acceleration, we use the kinematics equations. I'm not going to write them all down here. You can have them handy next to you whenever you need to use them. All right, so what about this horizontal launch kind of problem then? What does it feel like to actually do problem solving here? So I'm going to go ahead and just do an example for you. Let's say I'll do an example like what I just mentioned. Let's say we've got a table. Sorry, my table looks like it's sloping down a little bit. It's not supposed to. It's horizontal, like a regular table. And I got a ball that's rolling across the table. Let's say it's rolling at, I don't know, how about 7 meters per second? Right, rolling across the table at a constant velocity. Now, when it gets to the edge of the table, it's going to do this, right? So, also we would need to know how high is this table, and let's just say that it's, I think the lab benches in my room here are about 0.9 or so meters high. Right? Make that a 0.9 just to make sure you understand what that says there. Okay, so how are we going to deal? Well, first of all, what can we figure out? We can figure out a couple things. We can figure out how long, how much time it takes for it to hit the ground. That's fine. But probably the most practical thing we would want to figure out is where's it going to hit the ground. So somewhere around here, we're going to figure that from the edge of the table to wherever it lands. That's delta x, right? That's how far it goes in the x direction. It's x displacement. We're not interested in how far it goes on the table. We're interested in what happens after it falls off the table. Okay, so let's see what we can do to figure that out. When we have any kind of projectile problem, whether it's a horizontal launch like this one, or whether it's like an angled launch, which we'll get into in a few days, whichever the case, we're going to set up the problem in two parts where we have the vertical information. Usually we end up working with the vertical stuff first. It depends on what you know, but usually the typical projectile motion does this first, and the horizontal part. In the vertical direction, I use kinematics equations, which are, sorry, I'm not going to say what they are yet. You know what they are. But when I do a kinematics problem, you know what to do first, right? I was thinking which are the variables here. You make your list of these things. I'm not going to call it delta x. That would be a big, big mistake. This is the vertical direction. So just like in the free fall problems we were doing, the delta y, you need to call that delta y now. You cannot call that delta x because the x's are going to be over here with horizontal and time. Okay? Before I do anything over here, I'm going to fill out also here while I'm thinking about it. In the horizontal direction, this is constant velocity. There's only one equation that we need for constant velocity that I just told you about. Where'd that first page go? Only this one equation. That's it. Delta x is equal to Vx times t. So those are the things that need to be in my list. I need my delta x, my Vx, and my t. I'll tell you right now, one of the big mistakes that I see first-year physics students, such as yourselves, making is they want to list all 5 of these things in both columns. And that is just plain old wrong, because in the vertical direction, we have acceleration, right? You said, what's the acceleration? You know what it is. It's -10, gravity. It's the acceleration due to gravity around the surface of our planet. But in the horizontal direction, gravity is not playing in this direction. We get constant velocity, and that means we only have these 3 quantities to worry about, related by that equation. Right? You could write that equation down next to this every time. That wouldn't be a bad idea. I don't think you want to go writing down all of the kinematics equations every time, because that's a little too much. We'll decide which one we need when we get to that point. Okay, so once you have these things set up, you can put your -10 in there. It's going to be that every time. We need to think about what is going on with the launch. So my launch velocity looks like this. It's a horizontal launch, 7 meters per second, this way. So I need to look at these two things, the initial vertical velocity and the horizontal velocity, and figure out what needs to go here and here. Now, how much, look at this vector right here, look at the direction that this is pointing. How much of this 7 meters per second going this way is in the up-down direction, is in the vertical direction? How much of it? None of it. 0. How much of it is in the horizontal direction? All of it. So this is really, really important. Another mistake that students make very typically with this kind of problem is they see that 7 meters per second and they want to put it, they're like, oh look, there's velocities there, let's put it here. But it does not go here because this is the vertical direction. None of this is vertical, all of it is horizontal. Just to give you a little bit of a preview, I don't want you to put this in the notes right now. We'll get to this in a couple days. But eventually when we start like launching things at an angle, let's say my 7 meters per second was like this, and this was launched at 40 degrees, well then you've got a horizontal part and then you've got a vertical part. The horizontal part is the Vx and this is the Vi, right? So we'll get to problems like that. Obviously there's a little sine and cosine action there. But for right now, we're just dealing with horizontal launch problems. If you've got a horizontal launch, that is going to be 0. And the whole horizontal velocity is going to be here, right, in the horizontal column. All right, that is very, very important. What else do we know? Do I know? I'm just going to go through all of the variables that I don't have yet and see if I know any of them. Do I know the final velocity, the final vertical velocity when it hits the ground? No, I don't know that, and I don't think I'm really looking for that either. Do I know what the delta y is? Do I know what the up-down displacement is? Yes, I do. The ball starts here and it ends at the ground level. I'm only talking about the vertical part, so that's like this to this, right? Table to ground, or floor. Now that's going down, so that's going to be negative 0.9 meters. It's easy to forget that negative. It's going from here to here. And I don't know the time, but this is looking good. I've got three things here now. Do I know what the delta x is? No, but I would like to. That's what we're looking for. Do I know what the time is? No, but if I can find the time over here, then the time it takes, there's only one ball flying through the air. Whatever that time is, I can take this number and bring it over here. This is the only variable. If you look at the things in the list, this is the only thing that they have in common. That's the link. So if you want to get from this stuff over to here, you got to figure out the time and bring it over here. You want to get from this stuff back to here, there are some problems that are like that. You got to figure out the time, bring it back over here. That is the link. Okay? All right, so now we look through our kinematics equations. I'm like, okay, if I want to find time and I've got these things, which one should I use? So if you want, you could pause for a second and look at your kinematics equations, see if you can figure that out. Go ahead and pause, try to figure that out. Last chance, pause. It's this one. Important, I think, to write with delta y, not a delta x. So delta y is equal to 1/2 at squared plus vit. Delta y is negative 0.9. 1/2 a is negative 5. T squared plus vi is 0 times t, so that's 0 because of the vi. That's always going to be true for these horizontal launch problems because that's always going to be 0. And then I just need to do a little bit of math here. What's the square root? Show you what I'm doing. Of 0.9 over 5. The negative sign's canceled out. That's about 0.42 seconds. Now that's the time that applies to both parts of the motion. So I can take that 0.42 seconds and bring it over here. And now I've got 2 out of the 3 things for this equation. So I should be good to go here. So delta x is equal to Vx times t. Vx is 7. The time is 0.42. 29.4. 2.94. Yes. I'm going to call that 2.9. I've been keeping 2 significant digits different places, so I'll call that 2.9 meters. Right. So what is that? That is how far from the edge of the table it lands. And if you're thinking, yeah, okay, great, who cares? Well, this is actually one of the things in physics that has been understood for the longest time, back to the so-called Dark Ages, medieval times and all that. Do you know why? Because if you're going to get out your catapult and you're going to launch a big old rock at your buddy's castle, then you want to have the very best chance of hitting that. So because of like warfare stuff, all this projectile motion business is something that people were very interested in understanding. And for that reason, because they were interested, they developed pretty good understanding of it pretty early on. That compared to understanding forces and energy and stuff like that, this was much better understood much earlier on. I think that that is all you need to know. One more thing that I could do here is, if we were going to make a motion map of this, you'd have to make like a two-dimensional motion map, like starting when the ball was right there at the edge of the table. It's like right there. And then if we wanted to make a motion map, since the horizontal motion is constant, that means the dots in this direction would be equally spaced out, right? Because in the horizontal direction, it's constant velocity. But in the vertical direction, it's accelerating downward, so they'd be like getting further apart, just like we would do for a free fall problem. So like that's where the dots would be horizontally, and then this, in the vertical direction, they'd be getting further apart like that. So if you look, just kind of like you're plotting points, like it would be here, and then it would be here, and then it would be here, and then here. And if you wanted to make your little velocity things, they would point halfway. It's like you have two parts. You can draw in the horizontal part, which is constant. Vertical part, it's going like halfway down to that next thing. Horizontal part, those are staying the same. Halfway to that, like right, just in the vertical direction. Halfway to that, and then those are the same. That's how you could draw a motion map for this. I think you should be good to go. All right. Go launch some rocks at your enemies' castles.